Today, we will talk about the concept magnetic field in the chapter Magnetic Effects of Electric Current from class 10. So, you might all know what is a magnet. A magnet is a substance which can attract the other magnetic substances, right? That means it can attract the substances with the material made up of iron, cobalt, nickel, steel, and so on, right? Yes. Here on the screen, you can see a Bohr magnet, right? Let's say this is a North Pole and this is a South Pole. Assume that I placed a magnetic needle near a pole of a magnet. Let's say it is at 5 centimeters. It is kept at 5 centimeters. And you can observe that it get attracted towards the magnet. And then I just keep it at 8 centimeters. Okay. Now also I can see that it can attract it towards the North Pole. Now it is kept at 10 centimeters. In this case also I can see that the iron will get attracted towards the magnet. But when I kept at 11 centimeters, let's say I kept at 11 centimeters, it is not attracting towards the magnet. What does it mean? That is, a magnet can apply the force on the iron nail up to a certain distance. Let's say that is up to 10 centimeters of distance. If you place the iron nail beyond that distance, it cannot attract that iron nail. The reason is depends on the magnetic strength of this Bohr magnet. It can apply the force around it up to a particular region three-dimensionally, that is in all the planes. Okay. So if you place that magnetic substance beyond that area or beyond that region, it cannot attract that. It cannot attract that magnetic substance, right? So a magnet can apply the force up to a certain area. Let's say this is the area around the magnet, or else I will take like this. Okay. So here you can see that a magnet can apply the force. A magnet can apply the force in this area. If you place a magnetic substance at any point in this area or in this region, it can apply the force on that magnetic substance and it can attract it. But if you place the magnetic substance beyond this region, anywhere, that is surrounding the magnet three-dimensionally, this magnet cannot apply the force if you place a magnetic substance beyond this region, right? But if you place a magnetic substance within the region surrounding the magnet at all the planes, in XY plane, YZ plane, or ZX plane, that is three-dimensionally around the magnet, wherever you place the magnetic substance, it will be attracted towards the magnet. It will be attracted towards the magnet. Why? Because the magnetic force can be felt in this region by this magnet. Beyond this region, the magnetic force cannot be felt. So that we call this region or a space as magnetic field. We call the region where the magnetic effect can be felt is said to be the magnetic field. Magnetic field. Done. Yes. Here you can see. Here you can see a Bohr magnet is placed, right? A Bohr magnet is placed. And the iron fillings are sprinkled around the Bohr magnet. You can see that these iron fillings are arranged themselves or get aligned themselves in the particular pattern, right? You can see that curved lines around this. the curved lines of these iron fillings. And you can also observe that most of these iron fillings get attracted at their poles. They are crowded at their poles, isn't it? And here you see that how these iron fillings get arranged themselves around the Bohr magnet. You can see these patterns, right? Yes. So this alignment is depend upon the magnetic lines of force that are acting in the magnetic field surrounding the magnet. Magnetic lines of force are nothing but those are imaginary lines of magnetic force around the magnet in the magnetic field. We call them as magnetic lines of force. Okay. So here you can see that magnetic field. Magnetic field is the area around the magnet in which effect of magnetism is felt. As we discussed, the magnet can apply the force around it within a certain region, within the certain areas around the magnet, isn't it? So this area where the magnetic effect can be felt, we call this as a magnetic field. And the imaginary lines around these magnet in the magnetic field, we call them as magnetic field lines or magnetic lines of force. Okay. Yes. Moving further, we'll discuss about the properties of magnetic field or magnetic field lines. Okay. We'll see one by one. Initially, we say magnetic field is a vector quantity. Magnetic field is a vector quantity. You know that vector quantity is nothing but which has both magnitude and direction. So these magnetic field lines or magnetic field is a vector quantity which has both magnitude and direction. As it has magnitude, usually you can take the SI unit of this magnetic field is Tesla. The magnetic field SI unit is Tesla. As it has magnitude, it is measurable, right? As it is measurable, we need some unit to measure that. So that the SI unit of magnetic field is Tesla. Then, and next, before getting into these directions, okay, I just want to discuss about the magnetic lines around this magnet. You can see here, let's say I'm considering this a magnetic line, you can see that the arrow marks are given. How it is drawn? It is drawn from north to south, isn't it? Outside the magnet. And if you see this magnetic line inside the magnet, it is a continuous and closed loop so that it runs from south to north again. This magnetic line, which is drawn from north pole to south pole outside the magnet, will run from south to north pole inside the magnet. And here you can see that these are continuous closed loops. The magnetic lines of force around the magnet in the magnetic field are continuous and closed loops that has no beginning point and ending point. And you can see that outside the magnet, they are running from north pole to south pole, right? They are running from north pole to south pole. Similarly, here these magnetic lines, once they get into this Bohr magnet, they are drawn from south to north. They are drawn from south to north. Okay. Likewise. So outside the magnet, the direction of magnetic lines is from north to south. Whereas inside the magnet, the direction of these magnetic lines are from south to north. Okay. Now, if you see the distance or degree of closeness of these magnetic lines, you see here. As we are moving to the center of this magnet, the magnetic lines get separated or get moving further apart. But when you are moving towards the poles, they are coming closer, right? The degree of closeness is more. The degree of closeness, here you can see that the degree of closeness of these magnetic lines is more near the poles. But here at the center of this magnet, you can see that the degree of closeness of these lines is less. They are very farther apart. And most of the lines are crowded at the poles. And you can see here the density of magnetic lines is less at the center of the magnet, whereas density of magnetic lines near the poles is very high. It means the magnetic strength is maximum at its poles and minimum at the center of the magnet. Okay. And next, you can find no two lines will intersect at any point. You can see here, you won't find no two lines are intersecting at any point, right? Yes. Why? Because as they have, if let's assume that if they intersect, let's say two magnetic lines are intersect at one point, it means that at this point, at the same point, this magnetic line will have two different directions, which is practically impossible. Okay, so we can say that magnetic lines of force around the magnet in the magnetic field never intersect each other. Okay, yes. And as I told you here, the distance between the two lines, in the magnetic field is not uniform. The distance is changing as we move from one pole to another pole. But inside the magnet, as I told you, okay, they will run from north pole to south pole. Sorry, south pole to north pole. They will run from north to south outside the magnet, and they will run south to north inside the magnet. And now you can see that these two are parallel lines inside the magnet, so that the distance between these two lines is uniform. That means the magnetic force at any point between the lines inside the magnet is uniform. But outside the magnet, the magnetic force is not uniform. Okay, so that we can say that outside the magnet, you can find non-uniform magnetic field. But inside the magnet, you can find uniform magnetic field. Okay, uniform magnetic field. So these are the some of the properties of magnetic field lines or magnetic field. Okay. Now you can see these properties of magnetic field lines as we discussed. Let me recall the things. Here you can see that properties of magnetic field lines. First, we'll see that these are vector quantity. Magnetic field is a vector quantity which has both magnitude and direction, right? And the magnetic lines of force are closed loops. As I told you, they are continuous and closed curves, and they don't have any beginning or ending point. And coming to the direction, we have seen two different directions, that is outside a magnet and inside a magnet. If you take outside a magnet, the lines are directed from north pole to south pole. But if you see inside the magnet, they run from south pole to north pole, right? Yes. And as I told, uniform and non-uniform magnetic fields. So you can find non-uniform field outside the magnet. Why? Because the distance between the lines is not uniform, right? Inside the magnet, the distance between the lines is uniform. Okay, so inside the magnet, you can observe uniform magnetic field. Then, next, we also discussed magnetic lines of force never intersect each other or cross each other. Why? Because if they intersect, what does it mean? That is, it has two different directions at the same point, which is practically impossible. Okay, so they never intersect each other. And coming to the density of magnetic lines or degree of closeness of these magnetic field lines shows the strength of the magnetic field. Where you can find the density of field lines or degree of closeness is more. You can say that here at poles you can find a stronger field, so that magnetic field lines are very closer and density of magnetic lines is very high, whereas density of magnetic lines is very less and degree of closeness is very low at the center of this magnet, so that the magnetic lines are further apart, where you can find a weak field, but where you can find the strong magnetic field at its poles. So that the same point is again here crowded at poles, because magnetic field lines are most crowded at North Pole and South Poles. The reason is the magnetic strength is maximum at their poles, and whereas at the center of the magnet, you won't find such crowded lines. Why? Because the magnetic strength is weak, magnetic field is weak when compared to the poles. Okay. So these are all the some of the properties of magnetic field or magnetic field lines.